Continuing our investigation of sorting algorithms, in this video we are going to look at insertion sort. As you will see in this video, insertion sort, similar to bubble sort, is, first of all, the idea behind it is very simple, and as a result, implementing it is very simple as well. So it has a very short, few lines of code implementation, and it's easy to understand how it works and why it always sorts a sequence of elements. Now, what is the main idea? Let's start there. The main idea in insertion sort is the following. At any given moment in the execution of the algorithm, we see the array, the sequence of numbers, as two segments. The left segment is the part that is already sorted, and then the right segment is the part that is not sorted yet. And at every iteration, what we do is we pick the first element in the unsorted segment of the array and find its correct location in the sorted segment. So at every step, the size of the sorted segment of the array, I should say, increases by 1, and the size of unsorted segment decreases by 1 until everything is sorted. Okay, so to write it down, what we should say is that at every iteration, the first element in the unsorted part or unsorted segment of the array will be placed at its correct position in the sorted part. The sorted segment of the array. So an example would clarify what exactly we mean by this. So let's go through an example and do every step and see how this works, and then we will come back to the algorithm itself and actually implement this idea. Okay, so let's start with an array of integers of size 6. Okay, so the 6 numbers here are, let's say, 10, 3, 8, 19, 1, and 6. Okay, so index 0, 1, 2, 3, 4, and 5. So the size is 6. Now, as I said, at any iteration, at any given moment, we imagine that this array consists of two segments. The segment that is already sorted, which is on the left side, and then the rest of it, which is to be sorted on the other side. And if you think about it for a moment, it's kind of obvious that no matter what the first element is, if we consider only the first element, independent from what number you have here, the first element by itself as a subarray is always sorted, right? So at the beginning, the sorted segment of the sequence or the array has size 1, and then the rest of it is to be sorted. And as I said, as we go through the iterations, the sorted segment is going to expand, and then it becomes times 2, 3, 4, 5, and then the unsorted segment is going to shrink and become smaller and smaller until everything is sorted. Okay, but how does this work? As I said in the description above, the first element in the unsorted part, it's a special element for us, and we call it the key. So this is the key at the beginning, the first element in the unsorted segment of the array. And what we do is we find its correct position in the sorted part. So where should 3 be placed in this part? And obviously, because 3 is less than 10, it should be placed before 10. So here's what we do. We move 3 to the right to make room we move 10 to the right. We copy 10 here so that we empty this place for 3. And in any case, we end up with this. So 3, which was the key, will be moved to the beginning, 10 as the second, and then the rest of the numbers 8, 19, 1, and 6. 8, 19, 1, and 6 remain as they are. But now, if you think about it, you'll see that the first 2 elements together create our sorted segment. And then the rest of it, the other 4, are still unsorted, right? Now, the key here in the next iteration is going to be this guy. So this is the key. 8 is the key. And what is it that we do at every iteration? One more time here. The first element in the unsorted segment of the array, which is 8, will be placed at its correct position in the sorted segment. So 8 should be placed at its correct position here in the sorted part, which is between 3 and 10. Okay? But now, let me be a little bit more detailed in the description and tell you exactly how that happens. Because for us, looking at this array and saying, okay, yeah, 8 should go in between those two, it's easy to see. But how a computer does that? How can we implement this idea as an algorithm, right? That's important. And here's how it works. What we do is we have an extra variable called key so that we can store this value 8, our key. Okay? And then we compare 8, our key, with the last element in the sorted segment. Okay? And 8 is less than t, which means that it should go before. So what we do is, in this case, we push or copy 10 to the right. So 10 was here, we copy that here. And then we go to the previous element, 3. We compare our key with 3, and this time key is greater than 3, which means that this is the place that we need to copy the key, 8, and then 3. And then the rest of them remain the same. Okay, so now you'll see that the sorted segment of the array is increased in size again. Now we have 3 elements in the sorted and 3 elements in the unsorted part of the element. Okay, and you guess what the rest is going to be, right? The key is going to be the first element in the unsorted part. So now we update the value of our variable key so that key is 19. And we repeat the same process, which means we compare the key with the previous element, and if the previous elements are greater than the key, then we move them to the right to make room for the key until we reach a place where the element that we see is less than the key, and then that means that that's the place that the key should be inserted, right? And hence the name insertion sort. So let's do that here. So we kept the key in a separate variable 19, and then we look at 10, the last value in the sorted part, and we compare it with the key. Is 10 greater than key? No, it's not, which means that there is no need to push anything to the right to make room for the key. Key is fine where it is. So in this case, there is no moving around because 19, the key is already greater than every other element in the sorted segment. Okay, so now we see that the sorted segment has size 4. Now the unsorted part is getting smaller and smaller, and at the end, it will be empty. So still we have 1 and 6. Okay, I want to do this all the way to the end. If you got the idea, you can, skip this part, but for one example, I want to do this all the way to the end. So the first element in the unsorted part is the key. So my key is, in this iteration, my key is 1. Then I need to insert the key into its correct position among the unsorted elements, right? Now, visually, we can see that yes, it should go all the way to the beginning. 1 should be the first element in the sorted segment because it's smaller than all of them. But a computer cannot do that immediately, so we have to do this step by step. And here's how it's done. So, 6th position. There we go. I remember the value of the key in a separate variable. Now I keep comparing. Is 19 the last element in the sorted part? Is it greater than the key? Yes, it is. So move it to the right. Copy it to the right. So 19 from the 4th position goes to the 5th. Okay. 19 moves to the right. Then the next element is 10. Is 10 greater than the key? Yes, it is. So move it to the right. So 10 goes here. Next element is 8. Is 8 greater than the key? Yes, it is. So move it to the right. Next element 3. Is 3 greater than the key? Yes, it is. So move it to the right. From the first position, it goes to the second position. And now we are at the beginning of the array. There is no more element to move to the right to make room for the key, which means that the key should be copied here. So from this separate variable, we copy the key here. And now you see that we are almost done because the sorted segment has 5 elements in it. And obviously they are sorted 1, 3, 8, 10, and 19. And then the unsorted part has only 1 element left in it, which is 6. So this is the unsorted part. Now in the final iteration, the first and only element in the unsorted part is the key. Remember, the first element in the unsorted part is our key. And then we need to make room for the key in the sorted part. So first I remember the value of the key as a separate variable. So my key is 6. Then I keep pushing elements to the right to make room for 6, right? So first 19. Compare 19, the last element in the sorted part, with the key. Is 19 greater than 6? Yes, it is. So move it to the right. So 19 goes to the end. Next element 10. Compare 10 with the key 6. Is 10 greater than 6? Yes, it is. So move it to the move it. It meaning 10, right? Move it to the right. So 10 moves to the right. It will be copied here. The next element is 8. Is 8 greater than your current key? Yes, it is. So move it to the right. 8. Now 3. Is 3 greater than the key? No, it's not. So it means that this place is where you insert your key, and then the other 2 elements will remain as. So now in the last iteration, the sorted segment is the entire array. As you can see, it is already sorted now, so we are done. And then the unsorted segment is empty, and that means that we are done with this process. Okay, so just to repeat this one more time, we at any given moment we imagine that the array, the input array, consists of 2 segments: the left segment, which is already sorted, the right segment to be sorted. Then what we do is at each iteration, we pick the first element in the unsorted part, we call that the key, and insert that into its correct position among the sorted elements. And we do that by moving the elements that are greater than the key to the right, 1 position to the right, to make room for this element to be inserted. So here we only move 10 to the right and then write 8 in between, right? Now for the next one, we don't need to move anything because 19 is greater than everything. For the next one, 1, we have to move 19 to the right, 10 to the right, 8 to the right, 3 to the right, so that the first position is now empty for 1 to be inserted, and so on and so forth. So there you have it. That's called insertion sort. Now, in terms of implementation, how can we implement this? So if you think about it, there is 2 kinds of iteration going on. One is the iteration that moves the key to the right, and for for that, we can say that this is the first iteration, this is the second iteration, third, and so on, right? So there's a loop that changes the key from the element at index 1 to element at index 2, 3, 4, all the way to n minus 1, if n is the size of the array, the input array. So that's one loop, but then inside that loop, there is another kind of iteration that happens, and that is the one that, for example, if you look at here, the iteration that we repeatedly move the elements to the right. 19 goes to the right, 10 goes to the right, 8 is copied to the right, and 3 to make room for the key to be inserted. Right? So that's another loop nested inside the first loop that I told you. So we need nested loops to implement this, and let's see if we can do that. So we have the for loop. Oh, red. So they have the for loop that says for int I equals 0, I is less than n, where n is the size of the array, I plus plus. And then inside that, first of all, remember we store the value of the key in a separate variable. So whatever the type is, let's say int is the type of the element. And I'm going to call that key is equal to let's call the input array A at index I, right? Remember the I element is the key. And technically, we don't need to start from index 0 because if you remember at the beginning, I told you that the first element by itself is already sorted. So we can start as we did in the example from the second, I equals 1, right? So this is my first key, which is at index 1. Okay, so that's that. We remember that in an auxiliary variable called key. Then what I do is I define an index j, which is I minus 1. So this j here, if you think about it, is the index of the last element in the sorted segment, right? So if your key is here at index 4, then j is 3, right? J is here. Now, what we do is, if you remember, we compare the key with the previous element and the element before that and before that until either we reach the beginning, like what happened for this one, we compared it with these elements and one was smaller than all of them, so we had to move all of them to the right to make room for one at the beginning, which we did here. Or we do that, like for example here, we compare 8 with 10, and 10 is greater, so we move 10 to the right. But then when we compare the key with the element before that, then the key is greater than that. So we insert the key right there. So this process of comparing with the previous elements stops in two cases. Okay, so I'm going to implement that as a while loop. And I say while j is greater than or equal to 0, and a at j is greater than the key. Okay, so in this case, what do we do? First of all, we copy the element to its right position. So we say copy a j element at index j to index j plus 1. So a at j plus 1 is equal to a at j. So that's copying to the right. And then go to the previous element, so j minus minus, right? So that's the inner loop. So one more time to iterate on what we are doing here, we are looking at the previous element and we are saying if the previous element is greater than the key and we have not reached the beginning of the array, move that right there to the right, to its right position, and go to the previous element. So that's j minus minus. And at the end, when we get out of this while loop, it means that we are at the position that is the correct position for the key. So we just need to copy the key there. So a at j plus 1 gets the key at its value. And that's it. That's your code or pseudocode for insertion sort. Obviously, as a function, it needs the header, the parameters, and so on, but that's the idea. Now, I'm going to implement this and run it for you in a moment. Okay, here we go. This is the print function that we used in the first video or second video when we were talking about um, computing the runtime of the function. But here, first of all, similar to bubble sort, I'm going to use a template here so that the same function can be applied to arrays of different types. And then I have a void function called insertion sort. It has an array of type t as its parameter, the first parameter, and its size, obviously, as the second parameter. Okay, so here's the loop that I was talking about. For int I equals 1, I is less than 10, n, sorry, I plus plus. So that's my outer loop that moves the key to the right every time. And then inside that, I have my key. Key is going to be of type t again, right? Which is equal to a at I, the I plus first element. Then I have my j, which is I minus 1. So j is the index of the last element in the sorted part of the sequence. And then we have the while loop. So while j is greater than or equal to 0, and a at j is greater than the key, do the following. What is it that we do? We copy the element at index j to index j plus 1, like this, and then we go to the previous element, the element before that. And we repeat this until we either reach the beginning of the array or somewhere in the middle where the previous element is not greater than the key, which means that that's the location for inserting the key. And that's what we do here. There you have it. That's your insertion sort. Now, because I use the template to implement this, I can, when I'm testing it, I can test it on arrays of type int or double or character and so on. Let me just do one example. So let's say 12, 3, 14, 10, 100, and then 5 is my array. Now I can call print array once to see the array. What is the size? 1, 2, 3, 4, 5, 6. Looks like before calling the sort algorithm, and then I call insertion sort on ex1 and 6, sort it, and then call print array again. ex1 and 6. Okay, now we can run this. And okay, share again. And here we go. So you see 12, 3, 14, 10, 105 was originally the order. Then it changed to 3, 5, 10, 12, 14, and 100, which is the sorted version of it. Okay, so now let's go back to the whiteboard and talk about the time complexity of this algorithm. Okay, and that's the main reason that I wrote this here on the board as well. So, like the previous examples, again, I worked my way from the inside out. So let's take a look at what's going on inside the while loop. It's very simple. We have done this kind of arguments a couple of times now. So let me just say that what happens here, the time that it takes to do this, doesn't depend on how small or large your array is. So the constant time. Okay. Now for the while loop, you need to know how many times it iterates. And if you think about it, we cannot say exactly how many times, but we can say in the worst case, you if everything is already sorted and the last element in the unsorted part is the smallest element, which is not the case here, but imagine here instead of 6, we had 0. Then I have to, move 19 to the right, and 10 to the right, and 8 to the right, and 3 to the right, and 1 to the right to make room for 0 at the beginning, right? So that's n minus 1 moving around. So we can say that at most, n minus 1 is the number of iterations. But because we are using asymptotic notation and n minus 1, it doesn't make a difference because at the end of the day, we are going to drop all those details when we use the big O notation. But there we have it. So overall, for the while loop, we can say, overall, for the while loop, we can say it iterates at most n minus 1 times. Every time it takes this much time. So we can say c times n minus 1 is the time that it takes. Okay, at most. Because again, it depends on the numbers, how many times this while loop iterates. It can be different depending on the numbers that you have inside, but we know that at most it's this much. It cannot be more than this. Now, what's going on inside the outer loop? This is just a simple assignment, constant time. These are also constant time. So they're insignificant compared to this loop here. So let me just ignore those because at the end of the day, they're not going to matter. So what it boils down to is how many times this for loop iterates. And that's simple enough. That's just n minus 1 iteration. Because I start from 1, it goes all the way to n minus 1. So we have n minus 1 iterations of the outer loop. And then inside, we have some constant time things. And then this big thing, which takes t times n minus 1. So if we wrap everything and put everything together, what we have is that c times n minus 1 plus, and let's call this constant time here and these constant times here all together c prime. So this is what's happening inside the for loop for one iteration. And then this is repeated n minus 1 times because the for loop iterates n minus 1. So that's the overall time. And then if you just distribute and multiply, at the end of the day, what's going to be, it's going to be a polynomial of degree 2. And then if you drop the coefficients and keep only the term with the highest exponent, that will be n squared. So the running time of insertion sort in the worst case because here I said at most n minus 1, right? In the worst case is order n squared. So asymptotically is similar to bubble sort. Okay, so the final thing that I want to tell you about this algorithm is its best case runtime. Okay, what is the best that can happen? Now, the best case is when the array, the input array, is already sorted. Now, if the input array is already sorted, it doesn't have anything to do with the number of iterations of this outer loop because it doesn't look at inside the array, just as for I equals 1 to n minus 1. So that n minus 1 iterations are going to happen no matter how your array looks like. But this while loop here, I claim that is not going to iterate at all. It's just going to be constant time because if the array is already sorted, let me start with a fresh example. So assume that your input array is sorted from the beginning. Okay, so 4 elements, let's say. So it's like 2 and 10 and 17 and 100. So it is already sorted, right? Now, what is the job of that while loop? The job of the while loop is to look at the key and see if there is need for moving these elements around to insert the next element in. Now, since 10 is greater than 2, there is no reason to move anything. We are good. So we just increase I So 2 and 10 are now sorted. And then my key is 17. Again, the while loop says compare 17 with the previous elements, and if previous elements are greater than 17, move them to the right, make room for 17. But because the array is sorted, the elements before 17 are not going to be greater than 17, which means that there is no need to push any element to the right. We just move I one step further to the right. So now we have this situation. Again, similarly, 100 is greater than everything before it, so we don't need to do anything for the while loop. So in the case that the input array is sorted, this while loop, the condition is always false, which means that we never go inside, which means that instead of c times n minus 1, the entire while loop takes constant time. And you just check, and this condition is always false, and you immediately get out of it. So then, if you think about it, inside the for loop, we have this line constant time, second line constant time, the entire while loop also constant, and then the final assignment also constant. So we have a for loop that iterates n minus 1 time, and at every iteration, it does some work that takes constant time. So overall, what you get is some constant c prime times n minus 1, which is order n, because this is c prime n minus c, and then you drop the coefficients, and then between n and 1, n grows faster, so order. So to wrap it up, for insertion sort, here's the situation that we have in terms of its time complexity. For insertion sort, in the worst case, it takes order n squared, which is sometimes called quadratic time. And in the best case, which is when the input array is already sorted, and but still we call insertion sort on it, it takes order n time, because the while loop doesn't do anything, it's constant time. So linear time is called, right? So you see that asymptotically, in the worst case, insertion sort is similar to bubble sort, but in the best case, it's better than bubble sort, because if you remember for bubble sort, the best case runtime was also quadratic, also order n squared.